Let's look at some examples of how to draw these ray diagrams for spherical mirrors. And to do this, I'm going to show in PowerPoint how to find this. So in this first example, I have the object in red sitting at the center, and my first ray that I would draw would be from the tip of the object, parallel line over to the mirror, and then come back through the focal point, and the next ray would be from the tip of the object through the focal point, and then back parallel. And notice that my lines didn't quite cross, but it's the marker. It should cross back there. And this gives us our image distance, which is also at the center. Now we go through and do the calculations. I have the center is 12 centimeters. The focal point is 6 centimeters, just half of the distance to the center. My object distance is going to be equal to my center distance, which is 12 centimeters. And when I put this into my formula to calculate for the image distance, that's just the reciprocal of the reciprocal of the focal point, 1 over f, minus the reciprocal of the object distance. When I calculate that out, I get that it's 12 centimeters, which is what I expect. And when I calculate the magnification using this positive value for DI, positive value for DO, I get the magnification is -1. So this gives me my values for this image, and we see that for the center, the image is going to be at the center, and it's a real image because it's on the same side as the object. For the next, I moved the object towards the focus, and so here again for my ray I do a parallel, and then from the mirror I go back through the focus, and then I go from the object through the focus to the mirror, and then parallel back, and I get to my image. Now I can calculate this. I can calculate the squares, and I can find it out, or I'll take and say, okay, the center I reduced down to 6 centimeters. The focus I have as 3 centimeters. I put my object at 3/4 the distance to the center. That turned out to be 4.5 centimeters. When I calculate my image distance, I get 9 centimeters. And the magnification is just going to be the negative of the image distance divided by the object distance, and I get the magnification is -2. And if you look, you have 2 units for the object you have 4 units for the image. Now for the next, here I've moved the object in between the focal point and the tip. Now here's a good question. Why can't I put the object at the focal point? Well, let's run this and see. If I have the object distance at the focal point, I have 1 over the focal point minus 1 over the focal point, and that turns out to be 1 divided by 0, which means my image is at infinity. So I can't put my object on the focal point and still be able to see it. So here I put my object at 1/4 the distance to the center, and so here my center is at 6 centimeters, my focus is half of that at 3 centimeters, my object is 1/4 of the center, which is 1.5 centimeters. When I go to calculate my image distance, I get minus 3 centimeters. So that means that because of the negative, my image is on the back side of the mirror. So this is my negative side for my image. DO and F, my focal point, are positive. And my magnification, well, because DI is negative, the two negatives are going to cancel out, and I get twice the amplitude, or twice the height. And you'll notice that that's what I get. Here's 3, and here's 6. So to do the ray drawing, I'm going to start here at the object, and I'm going to go parallel till I get to the mirror, and then I'll go back through the focus, and then I'll just take and extend the line that I just drew through the focus back behind the mirror. Now the next line is going to be from the tip of the object through the focus, extend that up to the mirror, and then I'm going to extend back the parallel line, but I'm going to extend it on the negative side behind the mirror, and where those two cross is where my image is at. So I still use the same procedure from parallel to through the focus. I'm just going to extend the line back, and then I'm going to go through the focus to the mirror and go parallel back, and then extend that parallel line behind the mirror. So everything is the exact same for whether it's virtual or real. We use the same processes, same procedures to do it. Here we have a convex mirror. Here my center is minus 6 centimeters. My focus then is half of that, which is minus 3 centimeters. Remember that positive would be on the left-hand side. Here we're on the right-hand side. My object distance I'm going to put on the left-hand side at 1.5 centimeters. And as I calculate my image distance, it's going to come out to be minus 1 centimeter. And the magnification, because my image is negative, that's going to take care of the negative in the magnification, and so my magnification is a positive 2/3. And again, we'll draw the ray diagram. From the object, go parallel. And now I got to go through the focal point, but the focal point is behind. So I extend down behind the mirror through the focal point. The next line is going to be from the tip of my object towards the focal point, and I'm going to extend that down. And then from the mirror I would go parallel back, and I'm just going to extend that parallel line behind the mirror, and where those two lines cross is where my image height is. So just remember, parallel, then through the focal point, and then through the focal point and parallel. If you do that, you can do any of these drawings. You just have to remember whether to extend it behind the mirror or on the other side, depending on whether DO, DI, or the focal point are positive or negative. Now, just to illustrate a point, here I keep extending my object out, so everything center and focal point are the same, -6, -3. I moved my object point out, and now I'm getting closer to the focal point. And now my magnification is a half. Let's look at what happens if I go even further. -6 for the center, -3 for the focal point. I've moved my object out even further, and notice that my object distance is getting further, and my magnification's gone to about 0.4. So it appears that my image keeps moving closer to the focal point as my object moves further away from the convex lens. The question is, can the image go any further than the focal point? Well, we can find that out by just playing around with this equation. And let's say that we make DO go to infinity. And if DO goes to infinity, this term goes away. It's basically saying 1 over infinity is 0. And then I have the reciprocal of the focus, and in that case, that's as far as I can get. I can't go any further than the focus in this case. So that's our limit when we talk about the convex lens of how far the image can go based on the object going out to an infinite distance to the left. And one more example that you can look at. You notice that the image distance now is at -2 centimeters when the object distance is at 6 centimeters, and I'm down to 1/3 of the height. And so you can see it getting closer and closer to the focal point. It'll turn out that the image will have 0 height at the focal point, with the object being at an infinite distance. So review these ray diagrams, make sure you understand them so that you can do them for the homework. And they're very simple to do. It shouldn't take you very long to get them done.